This is part 6 of the series, The Basics of Geometry. In the last part, we talked about midpoints and segment bisectors. And we're going to start off this part with this quick example on how to use segment bisectors. So here we have line CD bisects segment AB, and we want to find the value of x first, and then find the length of AP. So here we have point P is the midpoint, because since CD is the bisector of that segment, it must go through the midpoint. So P is the midpoint, which means AP, segment AP, is congruent to segment PB, which means that the length of AP is equal to the length of PB. So that's all we have to do, is set these two expressions equal to each other and solve for x. So let's do it up over here. We say 7x minus 5 equals 9 plus 5x. Now we just subtract 5x from both sides. 7x minus 5x is 2x minus 5 equals 9. Add the 5. 2x equals 14. Divide by 2. X equals 7. So now that we know x equals 7, we're looking for segment AP. So we simply substitute this value of 7 in for x in this expression, and we have the value of AP. So we know that the length of AP equals 7x minus 5, which is 7 times 7 minus 5, 14 minus 5, 9. So this is pretty characteristic of a segment bisector problem. Simply set the segments equal to each other, solve for the variable, and substitute if necessary. All right, let's move on to the next topic. We're going to close out our discussion of line segments by talking about a concept known as partitioning a segment. It's sometimes necessary to take a line segment and divide it into two pieces that aren't necessarily equal, but where the two pieces are related by some particular ratio. Now remember that a ratio is simply a relationship between two numbers, usually expressed as a quotient. So one number divided by another. So let's look at an example here of what we're talking about. If I have some line segment AB, and I want to find a point P on that line segment AB such that the ratio of the lengths of AP to PB is equal to 3 to 1. That is, that AP is 3 times as long as PB. And the ratio can be pretty much anything. That's all we're really doing, is breaking this thing up so that we have a proportional relationship here. Now, the way this is done is fairly straightforward. That's all you really need to do, is take the coordinates. Assumedly, you're going to be given coordinates of your endpoints. You're going to be given the length of a segment, something that will allow you to determine the length of the entire segment. What you're going to do is you're going to take a look at your ratio. In this case, 3 to 1. That means 3 parts to 1 part. So our segment has to be broken up into 4 total segments. 3 here, 1 here. So the trick is, not really a trick, but the idea here is to break up your original segment into 4 equal pieces, 3 of which will be on one side of your target point and 1 on the other side of your target point. If the ratio was 3 to 2, we would have had 5 total pieces, and we would have had 3 pieces on one side and 2 pieces on the other. So that's really all there is to it. It's a fairly straightforward process. Let's go ahead and look at an example of doing this, just so that you can get a little clearer picture of it from scratch. In this example, we have a segment AB. The coordinate of A is 2. The coordinate of B is 12. and we're looking for the coordinate of a point P that's on segment AB that partitions the segment into the ratio 3:2. Okay, first thing we do is we determine how many parts we actually have to divide this segment into. In this case, it's 3 plus 2. So there's 5 total parts. Now the way to do this is you don't need to be super precise. You just need to eyeball it. So what I'm going to do is I'm just going to make little marks at approximately equal lengths and make 4 of them to break this segment into 5 equal pieces. So let's try 1, 2, 3, 4, 5. Okay, didn't work out too terribly great, but like I said, doesn't have to be perfect as long as we have 1, 2, 3, 4, 5 equal segments. Now, our point P, let's consider that our point P is going to be where the colon is here. So point P is there. That means there's going to be 3 pieces to the left of point P and 2 pieces to the right. So we have 1, 2, 3. That means point P would have to be here so that there's 1, 2, 3 pieces to the left and 2 pieces to the right. Now that's all remains is for us to determine how long each one of these pieces is so that we can determine what the coordinate of that point is. Well, the way we do this is by using the ruler postulate. You can do anything you want here. You could count, but ruler postulate is the easiest. Ruler postulate says the length of any segment, any straight line segment on a number line, the distance between any 2 points on a number line, is the absolute value of their difference. So 2 minus 12, which is the absolute value of negative 10, which is 10. So this is the length of AB. That's 10. Now, to find the length of each piece, we're going to divide that number by the number of pieces. And so since we have 5 pieces, we're going to divide this number by 5. So 10 divided by 5 equals 2. So 2 is the length of each piece. That means this is 2 units long, 2 units, 2 units, 2 units, and 2 units. Don't really have to do this. I'm just showing you for example's sake. Well, since we're going from A to B, we're going from A to B, there's 3 pieces from A to P and 2 pieces from P to B. So we start counting at A. Well, 2 plus 2 is 4, plus 2 is 6, plus 2 is 8. So this coordinate is 8. And you can see that 2 plus 2, 4, 6. 6 plus 2 is 8. So the answer is our coordinate is 8. That's the coordinate of our point P, and it divides this into the ratio 3:2. Just as a cross check, this length is 6. This length is 4. So the ratio of the lengths had better come out to 3:2. If we simplify this, 6 divided by 2 is 3. 4 divided by 2 is 2. So there's our ratio, 3:2, 3/2. All right, let's move on to the next topic. Our next topic moves us out of the world of points, lines, planes, very simple things, to a slightly more complicated thing called a polygon. And the first thing we're going to look at is what's known as a plane figure. Any figure that's drawn in a plane or a two-dimensional flat surface is called a plane figure, a figure that lies in a plane. Now, we're going to look at the idea of polygons. A polygon is nothing more than a closed plane figure with 3 or more segments known as sides. So here is a polygon. we're going to learn what this type of polygon is called. This is a polygon because this has segments as sides. This, on the other hand, is not a polygon. It's a plane figure because it's a figure that's drawn in a plane, if we want to assume that this is a flat surface. But it's not a polygon because a segment can't be curved. So anything with a curved face or a curved edge is not a polygon. It's a figure, but not a polygon. So a circle would not be a polygon. Now, we're going to need to classify these polygons, and there's two basic classifications. There's convex and concave. So let's take a look at that. Now notice, I basically took this polygon and drew it here in yellow, but if we extend each one of the sides into lines, you can see that none of the lines that contain the sides of this polygon have points that are inside the polygon. That is the strict definition of a convex polygon. A polygon in which no line that contains a side of the polygon has points in the interior of the polygon. So again, just extending the sides, you can see that none of these lines have points inside the polygon. Now, as a contrast, let's take a look at a concave polygon. Now, the idea of concavity is fairly easy. Just think of it as this polygon is caved in, like it hit a telephone pole or something. So this is caved in. But again, look at the sides and the extension of the sides into lines. Notice how this line does in fact have points in the interior of the polygon. This line has points over here in the interior of the polygon. So a concave polygon is a polygon in which one or more lines that contain a side of the polygon has points in the interior of the polygon. So that makes it concave. So again, a very quick visual. If the thing looks caved in, it's probably concave. Formally, if a line containing a side has points in the interior, then it's concave. Now, it's necessary for us to be able to classify polygons by their number of sides. So that's what we're going to look at next. Now, some of these classifications you've heard before, and some of them should be new to you. Obviously, a three-sided polygon is a triangle. Hopefully you knew that. A four-sided polygon is a quadrilateral. 5, pentagon. Penta is 5. 6, hexagon. 7, this is kind of a strange one, heptagon. Not septagon. A lot of people try to say septagon, but it's not. Heptagon is 7-sided. 8, octagon. 9, nonagon. And 10, decagon. Now you'll notice that most of these end with the suffix gon. A lot of people take this to mean side. We will use the idea side or angle. It actually means angle, that this has 5, 6, 7, 8, 9, and 10 angles, but we're going to call this sides or angles. It doesn't really matter. So 5-sided or 5-angled doesn't make any difference. Now we're going to add some things. Here we have hendecagon. So hen for 1, decagon. So 10 and 1. Dodecagon, 2 and 10, which is 12. Tridecagon. This KAI in the middle, that stands for and. So 3 and 10. Tetra. Tetra is 4. You may have seen the game Tetris. So that's 4 decagon. Pentachi decagon, hexachi. So just as you might think, it goes all the way through. And the last one that we're going to deal with is icosagon, which is a 20-sided polygon. Now, it's not going to be necessary to draw anything beyond, say, a 9-sided. You might not even have to do that, but it's important to understand what these names are. And you never know where these names are going to appear, so it's good to know them. All right, in the next video, we'll move on to our next topic.